Welcome to Sundar's lecture. This is lecture number 53, and in this lecture we are going to see Thevenin's theorem. Right? So in the last class we have told that we will solve some other problems or maybe some difficult problems by Norton's theorem, but we have started now with Thevenin's theorem. Let us know what is Thevenin's theorem, and we will take a common problem. Then we will solve by using Norton's theorem and also by Thevenin's theorem. Maybe we will take some dependent sources problem, so that it will be very difficult to find what is the current in a resistor or voltage across any 2 points. That we will see in the next class. Now we will take now Thevenin's theorem. So for Thevenin's theorem, it will be same thing, same thing. Whatever the procedures we have followed in the Norton's theorem will help us to know what is the Thevenin's theorem. Anyway, see, now we will take a linear network. We know this. So this linear network, there is 2 points in the linear network that is connected across the impedance. Maybe this is point A and this is point B, and this is that impedance, right? So the current flowing through this impedance, we are calling it to be I. Maybe IL, right? That is what we have considered in the Norton's theorem. Now, by applying substitution theorem, what we can do, this impedance can be replaced with this current IL, right? Do you understand? In the Norton's theorem, what we have done, this impedance we have replaced with a voltage source, and what is the magnitude of that voltage source? IL into Z. Now we will replace this impedance with the current IL as the magnitude. That's all, right? So it is very simple. Same thing, but with a different procedure. Right? So this will be the linear network, and this linear network, now it can be replaced with a current source. And what is the magnitude of that particular current source? That will be IL. This is point A and this will be point B, right? Now, what is our ultimate aim? We need to find what is the voltage across these 2 points. Now we have applied substitution theorem to find a new network, and in this network, if you want to find what is the voltage across these 2 points, first thing, by applying superposition theorem. Now we are going to apply superposition theorem. So now by applying superposition theorem, we are going to find what is the voltage across these 2 points. What is the first procedure? Let us keep all the sources in the linear network and deactivate this source. Right? That is the first procedure. So first maybe I will write it in a different color. First thing, deactivate IL source, and what we are going to do, activate all sources in linear network. That is the thing. In linear network, we are going to activate all the sources. So how our circuit will be now? So this is the linear network, and this will be now open circuited. Since this is the current source, if you are deactivating this current source, then what we will do? Obviously, we will open circuit this one. And what is this point? This is A and this is B. And what we are going to do now, then you simplify this circuit and find what is the voltage across these 2 points. And we are calling that voltage, it is VTH, Thevenin's voltage, or we will commonly call it is VOC, V open circuit voltage. That is the first one, the procedure. And what we will do now, the second thing, Now we will activate this source IL and we will deactivate all these sources. So activate IL source. Next thing what we will do, deactivate all the sources in linear network. Now I will draw the diagram. See, this is the linear network and this current source will be present. And which is point A? This is point A and this will be point B and this will be IL. And now you try to understand here only impedances are present. Only impedances. Why? All the voltage sources will be short circuited and all the current sources will be open circuited. That is what we have told. It has deactivate all the sources in linear network. Then what we will have? Only impedance. Solve that impedance. We will get only a single impedance across this point AB. Try to understand, right? So solve to find equivalent impedance in linear network. And what is that one? We have already seen that is ZTH, Thevenin's resistance, right? Thevenin's impedance, maybe Thevenin's impedance. Now our circuit will be, see, this is that impedance and we will have a current source and this is the current source, right? This is the current source and this is nothing but ZTH. We have solved this linear network impedance to find the equivalent impedance across AB. Right? This is A and this is B and this will be IL. And what is our ultimate aim? We need to get what is the voltage across these 2 points. And how our current is flowing in this circuit? This is the IL, right? A single circuit. And apply KVL between, not KVL, try to find what is the voltage between point A and point B. How will you find? So it will be VAB, we need to find VAB, then start from point B, go in this direction. See, the direction you are going and the current flow are in the same direction. Then what you need to put a minus, and what is the voltage? IL into Z, IL into ZTH. So that is the VAB, right? So we have found VTH here and we have found here what is the voltage in this point in here. It will be VAB will be is equal to what? VTH, because this is the open circuit voltage, right? Whatever the voltage we are getting here, that is nothing but it will be VAB now. And now we need to find what is the total voltage across these 2 points. What is the voltage across these 2 points in this circuit? In this circuit, what is that one? That is nothing but it will be IL into EZ, right? So, see, we know VAB should be is equal to IL into EZ, right? That is the thing we have found here. So, maybe across these 2 points will be IL into EZ. That is the voltage, not current, that is the voltage. Now we know what is the total voltage. That is nothing but it is IL into EZ. That should be is equal to, we know we have found two voltages. One is VTH and one is IL minus IL into ZTH. So that two voltages to be added by using superposition theorem. Right? We have found two different voltages. And what is this one? This one will be VTH and this one VTH. We have written. And this voltage will be IL into EZTH. Right? Now you simplify this expression. Maybe you bring IL to one side and you simplify this, finally you will get IL should be is equal to VTH divided by Z plus ZTH. So this is the final expression for finding the current in this particular resistance, that is IL. Now using this equation, I am going to draw a circuit. So first I will draw the circuit. See, there is a voltage source. There is a voltage source. There you have a series impedance that is connected across another impedance. See, I'm just going to write this is plus minus. Maybe you write it as VTH, and this will be ZTH, and this will be Z, and this is point A, point B, right? And what is the current here? You try to write it as IL. Then you see what is IL? IL will be is equal to VTH, and what is the equivalent resistance? That will be Z plus ZTH. So if you write the expression, obviously IL will be is equal to VTH divided by equivalent resistance, and equivalent resistance in the series circuit, that will be Z plus ZTH. See, same equation we have got here, and I have drawn the circuit with the help of this equation. And what is this circuit? This is nothing but equivalent Thevenin's circuit. So this linear network with the impedance connected between point A and point B can be converted into Thevenin's equivalent circuit with ZTH and VTH. And we know this one. We already seen these kind of problems in Norton's theorem. Now, this is the formula to find what is the current in the particular load resistance or impedance, maybe Z. So, we will take up a problem now. We will solve that problem, and by using Thevenin's theorem, so that we will get a good idea, right? So, we will take the same problem, maybe this problem again. So, now we have taken the same problem, and we need to find what is the current IL, maybe this is IL, across the resistance 4 ohms. And if they have given you like this, then obviously you need to consider this to be Z. Maybe this is the load resistance. Now, if you see the question will be find IL by Thevenin's theorem. Then what you do? Straight away you draw the Thevenin's equivalent circuit. What is the Thevenin's equivalent circuit? We know that it will be a voltage source. That voltage source will be connected across a series resistance that should be the ZTH, and this will be Z. We know this is the 4 ohms, and this is the point A, and this is the point B, and this has to be VTH, or we can call this to be VOC. Both are same, right? Now we need to find what is VOC, and we need to find what is the ZTH value, right? What is the formula? What is the formula of IL? This is the current IL, and this current IL should be is equal to VTH divided by Z plus ZTH. And we know what is Z now, and we need to find what is VTH, and we need to find what is ZTH. First we try to find what is VTH, or it may be VOC. So what is the procedure? See, if you want to find what is the voltage across these 2 points, that is nothing but it is VTH, and we need to open circuit, deactivate this current source, means we need to open circuit the load resistance. This load resistance will have to be open circuited, and whatever the voltage across this point, that means across point A and point B, will be the open circuit voltage or VTH. Now what we will do? See, we need to open circuit this resistance, and we need to find what is the voltage across this point. So I will draw the diagram. See, this is the voltage source, that is, now this has to be connected like this, and this has to be open circuited, and this is point A and this is point B, and we need to find what is the voltage across these 2 points, or this will be called as VOC, maybe point A and point B. This is plus minus 24 volt, and this will be 6 ohms and this will be 4 ohms. Try to understand here, this whole circuit will be linear network, and this is the load side resistance. Try to understand. Anyway, see now we need to find what is the voltage across these 2 points. So if I know what is the current across this resistance, then I will start from this point, go here, and we will reach point A, so that we will know what is the voltage across these 2 points. So for that, what you need to do, you need to find what is the current in this particular resistance. So I just consider this to be I. Since you see this is a single loop, here it is open circuited, so single loop. So if you want to find what is I, then it is very simple, right? 24 divided by equivalent resistance. What is the equivalent resistance? It will be 10 ohms. So 24 divided by 10 will give you what? It is 2.4 amperes. 24 divided by total resistance, so it will be 2.4 amperes. So I, which is nothing but it is 2.4 amperes. Now if I want to find what is the voltage across VAB, that means point A and point B, so or that can be considered as VTH, or it can be considered as VOC. So start from this point, come here, go here. So you see you are going in this direction, current is coming opposite to you, so it will be plus 4 into 2.4, and that's all, we have reached point A. Then if you simplify this, then obviously VAB, which will be is equal to VTH, and if you simplify this one, you will get it to be 9.6 volt. 9.6 volt. So we have found what is the value of VAB or VTH. So we know this one now. So now we need to find what is ZTH. So how will you find ZTH? Same procedure. ZTH procedure will be same for Norton's theorem as well as the Thevenin's theorem. See, to find ZTH, what we have done here, so this linear network, in this linear network, you need to deactivate all the sources in linear network, and you will have only impedances. That impedance, equivalent impedance will be ZTH. So if you deactivate, this is the linear network, right? In this linear network, you need to deactivate this 24 volt source, so it will be what? Short circuited, and you need to find what is the Thevenin's, what is the equivalent impedance across these 2 points, So how the circuit will be now? So this voltage source has to be short circuited, and this resistance will be available, and this is the point A and point B. So see, across point A and point B, this is 4 ohms resistance and this is 6 ohms resistance, and we need to find what is the impedance across these 2 points, and what is the impedance. And if you find this one ZTH, we can directly write ZTH, both are connected in parallel, these two resistors are connected in parallel, so this will be 6 plus 4, and in the numerator it will be 6 into 4. So this will be 24 divided by 10, and it will be 2.4 ohms. So now we have found what is ZTH. Now we can easily substitute, right? So IL will be is equal to, what is VTH? VTH will be 9.6 divided by, and what is Z? We know Z is given as 4 ohms. Z is given as 4 ohms plus, what is ZTH? ZTH we have found it as 2.4. So if you simplify this one, you will get IL will be is equal to 1.5 ampere. amperes. 1.5 amperes. So that is this one. What is this IL? It will be 1.5 amperes. Now you try to understand. So we have found these values. Maybe VTH. What is VTH? We have found it is 9.6 volt, and this value we have found it to be 2.4 ohms. This is now, these two values will be fixed unless, or you can say that even if this value, this 4 ohms is changed, these two values will be fixed as VOC and ZTH. So we try to get what is the current in this particular branch across AB if this 4 ohms is converted to 6 ohms. That is what we have done in the previous class also, right? You see, in the previous class, in the previous example, see, we have taken this example, and if this is changed to 6 ohms, we have found what is the current, that is 1.143, right? So now we try to understand, or we try to change this 4 ohms to 6 ohms. So we know now Z is changed to 4, Z is which is equal to 4 ohms, that is changed to 6 ohms now. And what is the current in this particular branch? So if you solve this problem by mesh current analysis or by nodal voltage analysis, then you need to find all things again to get what is the current across this branch. But now we know IL, which is equal to VTH by Z plus ZTH. We know what is VTH. What is VTH? It is 9.6 divided by this Z. You just directly put 6 here plus what is ZTH, that is 2.4. And if you simplify this, then obviously you will get IL is equal to 1.143 amperes. See, even if you change this resistance to 8 ohms, then you change this Z value only. So there may be many applications where only this load resistance will change with respect to time. And if you know what is the current in every instant when this resistance is changing, maybe this resistance can be a variable resistance. And if you want to know what is the current through this particular resistance or maybe impedance, then it is not necessary to find or not necessary to simplify this circuit again and again to get what is the current in this particular branch. You just put whatever the resistance value here in this particular expression, then you will get instant current through that particular resistance value. So this is how Thevenin's theorem can be applied to so many networks. So we know now how to find a current in a particular resistance in a circuit by using Norton's theorem as well as Thevenin's theorem. Both are a different procedure but ends up with the same current through resistor in a linear network. Right? So now we will take a different problem in the next class and try to understand Thevenin's theorem and Norton's theorem in depth, which means we are going to solve a dependent sources problem to get a good idea about Thevenin's and Norton's theorem. See, we will take up in the next class. Right? Thank you.